Okay. Got it. So we'll start. Hello?
Yes, please start now.
Okay, so today we'll be discussing on unambiguous detection of quantum Griffith phase. So Nikhil might be a bit familiar, but as expected, Alvay might be new. I don't know if he knows earlier. Anyway, so what is it? So before I get into this, so hello.
Yes, you are audible.
Okay, I thought somebody asked me something, so that way I start. Okay, so we know what is the phase transition. Phase transition is something which was introduced by Landau in 1970, and he introduced the concept of order parameter and a critical exponent and all that. So if you just look at this diagram, first diagram, so we have almost we all are familiar with the classical phase transition we often encounter in our daily life. Let's say ice to water or vice versa, or water to steam and or vice versa. So that technically, so under the name of classical phase transition often driven by thermal vibration or thermal disturbances. So if you can clearly see, this is the you can expect a sort of order phase. Okay, but when KBT is the order of this quantum nature, h cross omega, that vibration. So you may expect a critical region. That's what it has been mentioned in the blue shaded region as a classical critical region. Okay. Likewise, if you go to the opposite end, you can get h plus omega greater than KBT, where quantum disorder phase actually will sustain. So what is the quantum disorder phase? That means temperature has hardly anything to do with that. So it is the mostly dominant phase of 0-point fluctuation. Okay. But how about if they both are of same order or approximately of similar magnitude? So that is called the quantum critical regime. Okay. Putting it otherwise, the classical phase transition is often driven by the temperature. Temperature driven phase transition is known as classical phase transition. But on the other hand, if the phase transition is occurring in a system due to non-temperature or non-thermal parameter, suppose concentration due to doping or due to strain or due to pressure, all those parameters. And more important thing is here the phase transition could occur at absolutely 0 Kelvin, which is not possible to realize in classical domain at all. Okay, this is a very basic difference. So here I want to actually concentrate more on the magnetic material, because this is another very trivial and very well known example of phase transition. When a ferromagnetic material is actually getting into paramagnetic phase, then you can clearly see the transition could it is a second order phase transition, and you can clearly see that the order parameter diverges at the critical region. That is how the Landau introduced the phase transition, and they started the phase transition since the 70s, as I was explaining. But here, if you do know about very little regarding the ferromagnetic material, it's a long range magnetic order in a system. And if you can see this plot, this is how the magnetization falls as a function of temperature. Okay. But here, if you see, this is the magnetization actually falling as a function of carrier concentration. Okay. So sometime what you will find, a material is actually largely dominated by paramagnetic regime, or it's a paramagnetic in nature. That means there is no long range magnetic order among the spin. They are randomly oriented. However, actually there are some rare region, so to say, which actually exhibit some sort of interaction in a local region, which we call technically short range magnetic correlation. Okay, so this is what, if you see any conventional magnetic phase transition, the phase actually at the TC it doesn't fall like a step function, it never falls. So there is a broad transition, that means there is a range of transition, and even this magnetization plot doesn't actually sharply touch to the temperature axis immediately. Actually, it approaches the temperature axis asymptotically, and that is known as the telling region. Okay, this region, it is known as telling region. So in this region, actually, these are randomly oriented clusters of spins, which each surrounded region is known as a rare region, and you can clearly see all those four spins actually are arranged in a particular direction, and that too, it is a representation of the order state. Okay, even though largely you can see in the background all the spins are randomly oriented. So this page actually Griffith predicted, and that is why it is known as Griffith page. Okay, that means when a magnetic material, ferromagnetic material, actually undergoes a phase transition, it never actually immediately get into the paramagnetic phase. Before it get into the paramagnetic phase, it actually get through this critical and very unique phase known as a Griffith phase. But this is very much sensitive to the doping concentration, the system symmetry, and it is also very much prone to the magnetic field. That means if you do apply the strong magnetic field, the paramagnetic contribution to the total magnetization will dominate, and you won't see the presence of Griffith phase. But here, today we are going to discuss how unambiguously, without getting into the other very traditional experiments, so to say, let's say specific heat, magnetotransport, resistivity,
Candy? Candy, you are no longer audible to me. Is it audible to you, Nikhil?
No,
Oh,
I think his network connection is lost.
maybe I should. Can you please message him once?
Okay.
Oh, God.
I think he left and he will
He
join.
will again join.
hello,
Yeah, your connection seems to
Rahul
be
bhai.
very unstable, Prakash.
Yeah. So at what point I was not audible?
When you started that bullet,
Yeah.
Okay. So
That bullet
okay.
page.
So yes. Actually, I was more or less explain the introduction. What is the Griffith phase? How has it come into picture? And what is it as far as the magnetization is concerned or magnetic system is concerned? So these are the writing of all those points with some additional steps. So what I am essentially trying to say, the random theory explain the Fermi electron or the Fermi liquid theory. You know what it is. Here, the Griffith phase actually doesn't follow the Fermi liquid behavior. Instead, it is otherwise known as non-Fermi liquid behavior because it will have a different critical exponent nature and different universality class, and we'll see how it is. What I am essentially trying to say, without getting into the multiple conventional measurement or standard measurement, let's say specific heat, magnetotransport, resistivity, only by using magnetization, only by using DC magnetization, how one can unambiguously detect whether such phase exists in a system or not. This is what I just want to discuss. Of course, we will discuss towards the end what sort of role the digital play if one is interested to realize the Griffith phase in a system. Okay, am I audible, Ranbhai, now?
Yes, yes, you are.
Okay. So now, so let's say this is a system. This is a system. Let's say LSCSRMNO3.
No, you have
Okay.
not shared your
System is
screen,
immaterial. The message.
Gyanti.
Yeah, I have.
I cannot see your screen.
Oh, I see. Maybe I have to reshare it. So now can
It is coming. Yeah, now I can see.
okay. Okay. So see the figure one, left hand side figure. This is the MP plot or FCZFC plot. Now you can clearly see 60K. Clear? Hello?
Yes, yes, you are. You are audible.
Hello?
Yes, you are audible.
Okay, I thought I got again this thing. So since the transition is broad, we have taken the authors have taken the first derivative, and you can clearly see the transition actually somewhere around 260K or 274K. Okay, TC.
Mm-hmm.
So, but this field pool, zero field pool and field pool actually was measured at 500 oversted. So I told you at every point, I would tell you how we can unambiguously detect the existence of that Griffith patch, where some rare region exists in the background of paramagnetic system. Now we have observed it at 500 oversted. Let us observe it at 100 oversted and plot it as a chi inverse as a function of T. The inverse susceptibility, magnetic susceptibility as a function of temperature. You can clearly see this is known as Curie-Weiss law. You know, susceptibility equal to C by T plus minus theta omega C or CW Curie-Weiss. So from this T, you can clearly see this is your theta CW. Okay, theta
Mm-hmm.
CW, and this point actually is your Griffith patch. What do I want to say? Here actually we have gone to the transition at 250. Let's say this one 274. After that, we are expecting that the system should behave like para, but it doesn't. Actually, it will start to behave like para after 350K. But if you are analyzing a material in a conventional way, you will interpret it, the system has gone to the paramagnetic phase at 274K, which is wrong. That means even at 300 274K, in principle your magnetic moment should have been zero, but it is not. It will be exactly zero at 350K or well above that. Okay, this
Mm-hmm.
region 274 to 350, there is some clusters or local regions where the interaction among the very few number of spins does exist, and long range interaction among them have actually set up this critical state no matter it. Now what do? You apply the FC warming. Okay, now if you see, you can clearly see this intercept is now reduced. Now is no more intercept which exists here. This field inverse susceptibility, this field this plot has been measured at 20 kilo rested, and this is at 100 rested, which is very much this one. Okay, now you see this intersection is no more possible here because this is gone like this. So that clearly says, I was telling you in the introduction, the Griffith phase is very much sensitive to the strength of the magnetic field, because even though some rare region contributing to the magnetization, if you do apply the magnetic field of higher strength, paramagnetic spins or randomly oriented spins will dominate over these small clusters. That is why you don't see this critical regime or Griffith region. This is the first signature. Okay. Now, coming to the critical exponent study, we know that as per the Landau, the critical exponent or the order parameters at the critical point diverges or phase transition at the phase transition diverges, and it should follow. This is known as modified arrow plot. Okay, MAP. So this is H over M, which is nothing but inverse susceptibility. M over H is susceptibility. H over M is inverse susceptibility, which we have plotted over here. And this TC is Curie temperature, which is nothing but this temperature. Now, M is magnetization, we all know. This A and B are constant, and this beta and gamma, these are critical exponents. Okay, so this is what we can study. Here, in order to study that, what do you do? This is my transition I told at 274. So what you do, you actually measure, this is 274. You measure some MH, isothermal magnetization, above TC and below TC. So RF plot should have a positive slope, and you can clearly see this is a positive slope, and that is further confirms the magnetic phase transition is second order. Now what you do M square over H by M, which is nothing but RF plot, and you see every plot, every curve actually intercept y-axis in a positive y-axis. That clearly confirms there is a long range ferromagnetic order in the system. Okay, now you can clearly say this linearity at a higher temperature, higher field regime, and we can calculate the gamma and beta by using modified error plot, as I was telling, by using this equation and fitting this higher order field where the linearity sustains, or here. Okay, so this part we have taken, and you can clearly see this TC is 274, which is very much matching with this first derivative of this curve. Now beta and gamma is this. So for main field theory, there are different theory you can see here. For the reference I have put here, there are 3D Ising model where beta value has to be 0.325, gamma value is 1.241, and the delta is 4.82, and delta is known as Widom criteria. And this is 3D Heisenberg model where your beta, gamma, and delta value has to be like this. And the mean field theory, which is very much familiar to almost all people who are working in magnetism, it has to be like this. So you see, it is actually falling to this category, and you can clearly see at what value beta and beta is 0.61, gamma is 1.09. So it doesn't fall to any of this category. Therefore, it has been mentioned over here. Okay, it is neither falling to 3D Ising, neither 3D Heisenberg, neither main field, neither 3D XY. It is a totally new critical exponent obtained from the magnetization study, and this is known as Fisher curve. If you do want to actually calculate the critical exponent with very accurately and with a very nice error bar, we can go for this. And this is nothing but a straight line curve. You can clearly see one has to be below TC, one has to be above TC. Okay, so therefore you can see the different slope. One is positive slope, one is negative slope. And you can clearly see this is known as scaling hypothesis. What does scaling hypothesis say? Scaling hypothesis says the critical exponents or the order parameter varies differently before transition and after transition. And the critical exponent before transition fall to one universality class, and after transition they fall to another universality class. Therefore, you see in this plot they both are different. The critical exponent value at less than TC and greater than TC, they do not actually merge one over another. That clearly says there is actually transition occurring in between where some critical or very sort of Griffith phase is present, what we have already seen from the FCZFC. Now, these are the equations we have already used to calculate that. So first, if you at all want to know, okay, you are talking about the Griffith phase, can I quantify it? So if there is a way, yes, you can quantify TG minus TC by TC into 100. So how can you get that? Here you can get that. Here you have TG. Here you have TC 274 divided by TC into 100. So when you apply the magnetic field strength here, you have seen here the percentage of Griffith phase has been changed, and thereby you can actually quantify by applying the strength of the magnetic field of a different magnetic field strength, how you can actually change the percentage of that critical regime in your system, because it is nothing but TG minus TC. TC is fixed anyway to 74. This TG value will change because this curve, this straight line is actually coming downwards. You can clearly see. And for a 20 kilorested, you have no Griffith phase, so its case will be 10 kilorested, but you will get it less than that. Okay, you can quantify in that way. Now,
So, Gyanti, if I may interrupt.
yeah, yes,
So we are
yeah.
doing all these exercises in order to determine the various critical exponents like beta, gamma, etc. or delta.
Right.
Okay.
No, that is one thing. That is a
Mhm.
critical exponent study, and I have told you, actually the phase transition, whatever is happening, is it really happening at this temperature or not? Indeed, we can clearly see that below that temperature and above that temperature, which has been mentioned over here, is equal to 274, you have obtained two different universality classes. This is where the qualification to be called as a the system is following the scaling hypothesis, and it is actually the phase. The matter is actually undergone before transition and after transition fall into different universality classes. That's what it is. Requirement of quantum phase transition. But apart from that, as the title says, we are going to unambiguously always connect every measurement. How does it actually tell us about the presence of Griffith phase? That's what I am also saying.
Okay. And Gyanti, could you please also remind me about universality classes? Yeah, because I feebly remember it. I'm not able to recall it completely.
Yeah. Universality classes, that means they are saying the critical exponent, that alpha, beta, gamma, the how magnetization is falling as a function of susceptibility, falling as a function of temperature. All those critical exponents, alpha, beta, gamma, they used to represent. They will follow it. They will follow a single trend. They will have a one trend, and after transition they will have a different trend. And at the very much at the phase transition, order parameter diverges. You know that. And order parameter for the magnetic material is susceptibility. So that's why we are revolving about the susceptibility everywhere.
Okay.
So here also you can clearly see. So this is the plot. It is the traditional theory. So if at all you want to see, this is the paramagnetic contribution. This is the Griffith phase contribution. So Griffith phase component lambda always used to come between 0 to 1. So this is another indication.
So are these all your results? Have you obtained these results by yourself, or have you taken?
I have not published. So in IOP we have done all this thing on myself. But maybe next next time I'll show my result.
Okay.
It is very much one-to-one correspondence with that.
But no correspondence with whatever that has been found already in the literature.
Yes. I mean to say, the way people have been investigating or investigated so far, we have just taken, because people have investigated it from the various angles, like AC susceptibility, from specific heat, from magnetotransport, as I was mentioning. Let's suppose you have the experimental facility constraint. You cannot actually go around and do all this. If simply I have a magnetization data, can I say that unambiguously, without going anywhere else, without having any support, the system actually exhibits Griffith phase or not? My motto is that only by using squid magnetometer. That's it.
Okay.
So this is the RF plot. You can see, as I was telling, if you get positive slope, it is known as second order phase transition. Now you are getting negative slope. Okay. So So here what it says, there is no long range magnetic order present in the system, this inset. Now coming back to the IRM and TRM, this is known as a thermoremanent magnetization. What you do, you just cool the system from a temperature higher than the Griffith temperature. We have Griffith temperature 360. So let's suppose here the system has to be cooled down from 400 K, let's suppose, and come all the way to 5K or 10K, whichever the minimum you can achieve. At that, you just and while cooling, you just apply a field 100 arrested, let's say, and that field, once you reach the desired temperature, you switch up the field and allow the magnetization to randomize or decay as a function of temperature, and this is how it falls. Okay, if you see this one, can you see this red one? Hello?
Okay. So
Can you see this red one? Yeah.
yes.
This red one.
Mm-hmm.
It is very much similar to that, right? Very
Oh.
much similar to that.
Okay. And this is your result. So the slide you are showing, these are your results.
No. It is not my result.
Okay.
I am telling, I'll show you the replica of this in the next presentation, which is of course my result. I am just telling you how I have done something and followed some literature.
Yeah. Because whosoever sees it may get confused because you have not written down the references where you've taken these plots from. That's why I was asking.
Towards end, can I not give?
Perhaps it would be better if the references are given, because there might be many references that you have used, but let's say this plot is taken from reference one, the plot from the
It's
previous slide.
just one paper. Just one paper.
Okay.
It is just one PhD. So I can give that paper.
Okay.
Just one paper.
Mhm.
Okay. So this awkward turn indicates the presence of Griffith phase, and if you can plot the reverse, you can get this kind of thing, which is of course as expected. Now this is another beautiful experiment. This is known as IRM, isothermal remnant magnetization. What do you do? Very much like that. Here we have cooled the temperature from above 350 or 360. Cool the system down in the presence of magnetic field, reach the desired temperature, allow the system to decay its magnetization as a function of temperature. Instead of decaying as a function of temperature, allow the system to decay as a function of time. That's what it is. So at a particular temperature. So at 300K, 320K. And by using this equation, as the theory says, this equation says if the system follows this one, this is for the Ising system, and this is for the Heisenberg system. It follows the Ising system. You can clearly see. It doesn't follow stretch exponential or Heisenberg. That is another indication the system exhibit actually a very feeble magnetic interaction, though transition has been occurred. The magnetic phase transition has been already done. Okay, so am I audible, Rahul bhai?
Yes, you are.
Okay. So now coming to another one. So again FCZ FCA, what we have already done. This is another theory, another group of theoreticians. They have proposed if your system exhibits Griffith phase at a particular temperature or regime, this should follow this trend. Your curve should follow this trend. If you do not have a feel for it, you can see this one, this person, 300 to 350. The black curve. Can you see it all way? Black one.
Yes, I can see.
Yeah, this is black one. We have zoomed, and from 250 to 350, 360, let's suppose 250 to from here to here, they have taken and they have tried to fit this equation. And from here you can clearly see if you are actually claiming there is a rare region which is responsible for the existence of some sort of ferromagnetic interaction. Can you tell me that cluster magnetic moment? Of course you can tell, and this cluster magnetic moment can be derived from this C prime value. Okay, this C prime value will tell you the cluster magnetic moment. Hello?
Yeah, can I have a question now?
Yes.
So is this model that MTH proportional to exponential whatever, is this model
Yeah.
phenomenological or does it have a derivation from, let's say, basic principles? Is this phenomenological?
Yes. Yeah. It is.
Phenomenological.
It has not. Yes. 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 It is phenomenal.
Okay.
So
Okay.
again, if you have a magnetization data at low field region, at a high field region, it doesn't fill to the Brillouin function. Brillouin function is nothing but the function which explains the magnetic system after phase transition is occurred. So in the paramagnetic region, Brillouin should fit quite well. You can see, as I was claiming, means the authors have claimed the Griffith phase sustain up to 360K, above 360K, the system has actually become para, and you can clearly see it is started actually fitting with the Brillouin function. But above that, it doesn't fit actually at a low field as well as at a high field region. That another indication that actually the complete phase transition has not been occurred so far. In principle, the moment has actually not gone down to real zero. There is some finite magnetic moment value still persists. And this is another beautiful theoretical claim. If you do take the first derivative of magnetization data, this MS plot, and from above Griffith phase and below Griffith phase, you see once you really reach the Griffith phase, you will find the linearity. It's very surprising. You don't find any such tendency if you are dealing with conventional ferromagnetic material which doesn't possess this phase. So this is another trademark signature, how you can confirm Griffith phase existing in your system or not. Okay, very simple, but very nice way to unambiguously check. And this is another one which I certainly do not want to get into this. I have already told how it has been fitted. But this is another beautiful thing. If you are going to actually check whether that small magnetic moment is coming from super para or it is actually Griffith phase, this is the test. You check it M by ms as a function of h by t plot, and you find they do not actually fall one over another. Had it been otherwise, that means if they would have fall one over another, the system would have claimed to be a super paramagnetic phase. But it is not the case. Instead, it is a Griffith phase. Okay. So, and this is some additional recipe, which is of my interest as far as magnetic resonance is concerned. You can clearly see if the ferromagnetic system, you can clearly see a broad transition like this. Instead of the paramagnetic transition, there will be additional feature. So people have explained it very nicely and naively by considering resonance. So I think I am done.
Okay. Thank you for it. So what was X in the previous slide? Perhaps I missed. I mean the formula. So you've written X equals 0.15, X equals 0.2. What is X in here?
Yeah, those are actually the concentration.
Concentration. Concentration of?
Yeah, I told you, man. Concentration. Let's suppose I have a system LaCa MnO3, lanthanum calcium manganate.
Okay.
Okay, LaCa MnO3. So
Okay.
here, let's suppose I want to introduce the decoder. So what I need to, let's suppose in place of calcium, I have add some amount of strontium, Sr.
Both are second group
So
elements.
that is the concentration of Sr. Let's suppose. So it is a concentration of doping. You can take it in a generic sense. It is the concentration of doping. Yes.
Okay. Sure.
So people actually have investigated the Griffith phase from various angles by employing many experimental techniques. But here, by considering the constraint to a given student or to a given circumstances, if at all one is actually encountering the situation, how one can unambiguously claim without getting to a fancy experimental facility that this is what is certainly there. This is, I found, much more useful for the learner who actually trying to investigate some phase transition, which is very rich, of course. Quantum phase transition is very rich on its own account. So that is why I thought at least it would be useful for the people who are working on magnetization or magnetism.
Okay. Can I also ask one more question? Perhaps it might sound very weird.
Please.
So, like, what is the motivation for studying Griffiths phase? Or maybe you told it in the beginning, or maybe I missed it. But
No, I haven't.
then
I
why are we
haven't.
studying
No,
it?
no, no. No, I haven't. It's a great question, a $1 million question, but answer might be one. Means not that convincing, as I also am not convinced so far. That this is the phase or this is the region, it will give you much more fundamental idea about the system. I haven't found any sort of use of this material or particularly this page so far. It will just give you to putting it otherwise, it is of academic interest.
Okay.
It is of academic because Rahul bhai, you see, people are studying spin frustrated magnetism. What is the use of frustrated magnetism? It is almost of no use so far. In future, what will come, nobody knows it beforehand. But at present, if you are asking me, so I can simply say that considering the limitation of my knowledge, I beg pardon if I am missing something. But as far as I know, it is of academic interest. It will give you a lot of good fundamental understanding about the system.
Okay.
Regarding the phase transition.
Okay. Fine.
Yes.
Okay. Thank you. So, does anyone have any other question?
No, not from my side.
Okay. Okay. So
Okay.
maybe I can ask one more. So what is the meaning of averaging over mu in equation number 12? Or is this kind of average?
Yes.
So
This is just
is it
a
averaging over what? Time or space or what?
No. Here you see, it is actually spatial, means a distance.
Okay.
So,
Averaging over space.
Here you see. Okay. This size won't be different, same, na, for all. For a given temperature, this size won't be same. This size might vary. Na? Are you getting my point or not? These rare regions, size may vary as a function of temperature. So what we are observing in our experiment is just this plot. So whatever moment we are getting, whatever moment you are getting, we are actually averaging and multiplying it. So we are taken average of all those. One might be small, one might be big. It is the average of all which will satisfy this plot. We can calculate the number of clusters, we can calculate the total magnetic moment, but we do not know the individual magnetic moment of individual cluster size, because the size of the cluster may vary. That's what it is. It is the size average.
Okay, fine.
That's why this is the average cluster moment.
Okay.
Yeah.
So if there are no further questions, so let's decide who is going to talk the next Sunday. I'm stopping the recording now.